Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so we are very delighted to introduce Xiaogang Wang. So Xiaogang is a professor of electronic engineering in Chinese University of Hong Kong. His group has worked on deep learning and computer vision and has done many great works. In particular, his group achieved near human performance in face recognition, such as over 99% in label faces in the wild data set. And also his team has achieved top entries in large-scale object detection challenges in recent years. So today, Xiaogang will talk about deeply learned face representation.
Okay, thank you. I'm going to talk about feature representation for face recognition. So in the past 2 years, deep learning has boosted the performance of face recognition substantially. So on the well-known face recognition benchmark, LFW, and the face verification accuracy has been improved from 96% to almost perfect, and even surpassing the human performance on this benchmark. So in this talk, I'm going to briefly talk about how to learn the face representation from the classification and multiview reconstruction task. And given the high-performance network, I'm going to present some empirical study on the properties of the neural responses. And making use of such properties will show that we can make reduce the size of the network substantially while keeping the recognition performance. It also has some other interesting applications. So currently, the most common way used to learn the facial representation is through this identification task. Basically, given an input training image, goes through the ConvNet, it's classified as one of the large number of face identity class. And so in the top layer, the neurons in the top layer, they are the feature representation we want to learn. So they capture the rich interpersonal face variations because they need to classify a large number of faces, and they are discriminative, and also can be well generalized to new identity outside the training data. So also on top of it, we also add the verification signal. So basically, if you have two images from the same person, will require their learned feature representation to be similar. So this verification and identification signal, they are jointly added to the multiple layers to learn the feature representation. We can also learn the face representation through reconstructing multi-view representation. We know that in face recognition, the view variation is a major factor affecting the performance. So we, in this network, given an input image in the arbitrary view, we want to reconstruct all the viewpoints of the same person. And here I'll show you the examples. These are reconstruction results, and these are the ground truths. And the training and the test data, they have no overlap on the identity. So in the network, the identity and the view representation, they are represented by different sets of neurons, so you can separate the identity features and the viewpoint features. Also, the viewpoint has a continuous representation. So this is our network structure. The X and Y, they are input and output face images in different viewpoints. And this HID, they are the neurons encoding the identity information of the input image X. It removes the viewpoint information from X. They are the deterministic neurons. And this HV, they are the random neurons encoding the viewpoint information of the output image. They are sampled from uniform priors. And this HR, these are neurons encoding the features of the output image Y. So it combines both the identity information and the viewpoint information. Actually, this you can see this network is a combination of deterministic neurons, also random neurons. And this HV, this V2, these are the identity features. They are useful for face recognition. And this viewpoint label can be inferred from output image as well as from these random neurons encoding these viewpoints. So we can use EM to update the probabilistic model on the network. It corresponds to the forward and the backward propagations. So at each step, we infer the values of the random neurons, which encode the viewpoint information. And at M step, we use to update the parameters of the network. And because we have a continuous view representation, and we can interpolate and predict the images under the viewpoint unobserved in the training data. And in this example, our training data only have 0 degree, 30 degree, and 60 degrees. In A, we want to reconstruct the image, face image under 15 degree and 45 degree new viewpoints. And these are reconstruction results, and these are the ground truths. And in B, our input image under the 15 degree and the 45 degree, we want to reconstruct the frontal view. You can see that even we observe some new viewpoints because we can interpolate the images, they can be reconstructed well. So actually, this idea can be also generalized to other factors besides the viewpoints, and such as the ages, expressions, lightings, etc. Actually, you can also jointly consider multiple factors. Here, I give you an example. Given an arbitrary face image as input, we can reconstruct different combination of the poses and the expressions. And in this example, we construct the face image on the different combinations of lightings and expressions. And given this high-performance neural network, and some people think this deep learning is you simply use a large number of parameters to feed the data. So we are interested in study the properties of the response of the neurons. And actually, these properties are naturally owned through large-scale training. We don't add explicitly add some regularization to the model. Here, given an input image, and we look at the neural response in the top hidden layer, and then you can see that some neurons are responded and some have no response. It's not surprising we have this sparse representation because we use rectified linear units as activation function. If you add some occlusion and change the viewpoints of the same person, we observe that this magnitude could be can change to some extent, but the activation pattern could be is relatively stable. And if you change the identity of the person, we find out the activation pattern, 0-1 pattern, is going to be changed substantially. So this inspires us. We just use the binary code from this activation pattern for face recognition, and the result is pretty promising. We still, even you use this binary code, we still can get a very high face recognition performance on over 99%. So this implies that the activation pattern may be even more important than this magnitude. Also, it has it's important for applications because if you use this binary pattern for recognition, it's going to save a lot of storage and also the computation time. So if you look at the input test image, and we observe that about half of these neurons are responded and the other half have no response. So if you want to compare the Hamming distance of the activation pattern from two face images, and this moderate sparsity response can give you the maximum distance between these two images. On the contrary, if you have the face representation, which is highly sparse, most of the neurons has 0 response, and then their distance will be small. You're going to waste a lot of bits. And if you look at a particular neuron, we observe that on the test image, and about half of the image have responses, and the other half have no response. So it means that it can maximize the discriminative power, maximize the entropy of this neuron on describing this test image set. But if we look at a particular person, for example, in the LFW, George Bush has 500 images, and you can find some neurons which always always respond to George Bush, right? And you have some other neurons which always has zero response to Bush. So our training data and the LFW have no overlap on the identity of the persons. And the similar thing also happens to the attributes. You can find some neurons that always respond to the female male faces, have no response to female faces. So we found out that these neurons, they have a strong selectiveness on the identities and also the attributes. And here we show you some example. This neuron always have the response to Bush, and this neuron always have no response. And we show you more examples on most people. And this also happened to the identity. And these neurons always respond to male faces, always have no response to female faces. They are on the contrary. And these are the race-related attributes. For example, this neuron always responds to white people and no response to other attributes related to the race. So this means that if you want to classify a single person from others or recognize a single attribute, you probably can find a particular neuron which can have a very high recognition accuracy, even with a single neuron for recognition. And on the contrary, if you compare with the high-dimension LBP, you'll find the best single feature from LPP for recognition. The recognition rate is only 60 or 70%, quite low. Now we can also look at all the neuron responses. Here I sort these neurons according to their average response according to the particular person from large to small, and then we can keep the order and look at their average response to all the other images, and we can see that it's a kind of a pretty uniform distribution on the other remaining images. And if you look at their recognition accuracy on with a single neuron, and then we find out, of course, these neurons, they have good recognition capability on Bush because they always respond to Bush. And these neurons, they also have good recognition accuracy because they always have no response to Bush. And in the middle, you'll find some neurons that have a lot of uncertainties, right? So, but in comparison, and for high-dimension LBP, if some feature have a high response to a particular Bush, a particular person, they also has a high response to other images. They are not good for recognition. And here we also can visualize the neuron. So for each neuron, we divide the images into 3 groups: high, middle, and low response, and calculate the average image in each group. And then we can see that each neuron have clearly semantic meaning. For this one represent the gender, age, etc. So because of such make use of such properties, we can actually simplify the specified network structure. As I mentioned, because they have selectiveness on attributes, if you want to recognize a particular attribute, you only need a very small number of neurons, and we can remove a lot of edges. And this is also happen to, we can explore the correlation between the neurons in different layers, right? So if you want to predict a neuron at a higher layer, you only need to very few number of neurons from the lower layer. And so you can remove many this kind of connections. And so we propose to alternatively optimize the learning weights and also the structures. Okay, you train a dense network and specify the first layer and retrain the network, and then specify the second layer, and so on. Okay. Yeah, I'm probably running out of time. I just give you the final result. And this one is you start with the denser network, and this is a sparser network. It only takes 1/8 of the amount of parameters, but we got even higher recognition performance. I'm going to skip all the remaining parts. So in summary, I'm introduce how to learn the face representation and also talk about some empirical study on the properties and also make use of such properties so we can make the network smaller. Okay, thank you.
Thank you. So, yeah, we have some time for questions. So if you have any questions, can you come forward in front of the mic?
Have you tried this on larger data sets where the pruning might hurt because you're less underfitting?
You mean the property of the neurons or the whole algorithm?
The pruning is probably helpful because you're working on a small data set, right?
We don't have a special. We just regular the pulling layers.
No, the pruning, so removing edges.
Oh, okay. Oh, yeah. Not having, but this so far this training data we have 400,000 training images. It's training data is still pretty large. Yeah.
So do you have any idea how to, so what are the limitations of the current CNN that you're using and how, what do you think is going to be the frontier and in the next 2-3 years, what do you think you're going to work on and to improve?
Okay, yeah, I'm quite interested in how to make the network smaller. So this, we know that it's particular on face recognition, we have very good recognition performance. But if you want to apply this to some mobile phone and camera to the front end, and then you want to you need to make it smaller. And also we find this kind of joint learning the weights and also the structures could be quite effective. And so that's one of the things.
Over there.
So in some of the early deep ID work, you guys were using key points. Can you comment on the importance of key points? And are they required, not required? What is your most recent work?
So the key points feature. So we use in the face recognition because we use multiple models. So basically we crop multiple regions for each region to get the feature and then to do the prediction to the average. And if we need to crop multiple regions, then we rely on the key points, kind of handle this misalignment. But if we only use a single model, single region for the face recognition, we only do very simple geometric normalization, rely on 3 key points. Yeah.
Hi, this is really good work. Can I ask a little bit about pruning? Since we also experimented with CNN RSTM, and I'm curious on face recognition tasks, how many % of the parameters can be pruned, and what is the heuristic?
We could remove more than 80% and still get even higher performance.
And what is the heuristic you use for pruning?
So basically, you start training a original network, and you got the weights, and then you know the correlation between different neurons, and then you remove some connections which has weaker correlation in the first layer, and then you retrain the network, and then you specify the second layer, and so on. So do this iteratively.
So when you are sparsifying the first layer, the rest of the layers are fixed to be densely connected.
Right, we fix it, and then we retrain the network, and then the second layer.
Okay, thank you.
So in the first part of the talk, you had stochastic latent variables representing pose and viewpoint and whatever, and then you used an EM procedure, and then you went on to just have a fully deterministic feed-forward network as usual and train it with SGD. When that second approach seemed to discover latent attributes, could it also discover latent viewpoints? In which case, do you need the hidden variable method? What are the pros and cons of those?
So in first one, we do have this kind of random neurons because we need to represent this viewpoint information in a continuous way. So we have this probabilistic model on this random neurons. I'm sorry, what's the second question?
Well, so in the second part of the talk, you're discovering latent attributes like gender and so on.
Right.
Let's say gender is a bad example. Let's say race, which you could think of as a continuum. Viewpoint is also a continuum. Does it discover the viewing angle of the face organically, even though it wasn't labeled?
No, actually the second part discovers the properties. We are based on this. We didn't use. We only have the deterministic neurons. We don't have. It was not based on this multiview face reconstruction. Yeah.
Okay, so we have one more. Yeah, last question.
Do you have any thoughts on using this for anomaly detection? Like, for example, if you wanted to detect a mole on a face, but you didn't have any, or you had a very small amount of mole training data, or even.
Sorry, can you repeat again?
Oh yeah, sorry. Do you have any thoughts about using this for anomaly detection? For example, detecting moles on the face?
I haven't thought about it. Right? No, I guess this kind of example very rare in the training data, and I think for the current representation probably is going to be hard. Is because they learned from the normal faces, and what he was saying, kind of some abnormal regions, right? Yeah.
Cool. Thank you.
Okay, thank you. Let's thank Xiaogang again.
Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.